So thanks everyone for joining this talk on Apache Hudi for the next generation of AI. So a little bit about myself. I'm actually a senior software engineer at Onehouse, which is a data startup that's actually organizing this conference. I primarily work on open source data infrastructure. So I made contributions to Apache Hudi, Apache Iceberg. I'm a PMC for Apache Xtable, and also I made contributions to Polaris. And with me is my colleague, Tim. So he's a data infrastructure engineer at General Intuition, which is one of the research labs working on world models. He's a committer to Apache Hudi and also to Apache Xtable. So before I talk about Hudi, I think it's important to just kind of have a bird's eye view of this entire AI landscape in 2026. So essentially, these models from the frontier labs have gotten very good at general reasoning tasks. And the agentic products that they release, things such as Claude Code or from OpenAI Codex, essentially have allowed us to do things such as code execution, code reviews, email automation, or drafting a design doc. So essentially in 2026, if you're an enterprise, you've enabled your employees to leverage these agents to carry out any kind of cognitive task. And the question becomes, how do I ensure that my agent, if I give it a task, that it can actually perform accurately and not go off the rails? And the fundamental answer to that question is data. Essentially, you need to provide your agent with high quality data source, and the systems needed to actually store this new types of data as well as the search patterns for agents. So what I mean by this more specifically is data now has two shapes. If we think about data, at least for the last 2 decades, it's primarily been tabular information. So you're storing things such as integers, floats, some kind of timestamp data. And the type of access patterns you're using to query that data is primarily doing pruning out specific columns, doing some type of aggregation like a group or join, and scanning large amounts of rows within your table. If you think about agents, though, they fundamentally aren't just querying tabular information. For example, you might be providing an agent with some screenshot, so an image, or some kind of video file, or maybe the audio transcript of a customer review for a product you have. And in your system, you also have to store the actual embeddings, which is basically kind of like a numeric representation of an image or audio or video that a computer can reason on. So fundamentally, the types of data you're storing is much larger because instead of it being maybe bytes or kilobytes of like an integer or float value, you're storing these larger images, videos, etc. Specifically, also the search patterns have changed now. So instead of doing these OLAP analytic style queries, you have a new pattern like training a model. So in order to train a model, instead of doing sequential scans, your model needs to basically very quickly find samples within the table and being able to have fast random access to actually index into those values. If you are an enterprise that, let's just say, trying to establish within, let's just say, our customer reviews, the frustration between one review versus other reviews, you're not doing a select or a filter on an exact match. You're trying to find the semantic meaning between these two different reviews and their similarity, essentially. So in practice, what's happened now is the data ecosystem has become fragmented. So essentially, you have different systems for storing different types of data, and these systems catering towards different workloads. So vector databases like Pinecone and Viviate have become very popular because they've become very useful when it comes to storing these vector embeddings and then providing an API like a vector search functionality. If you look at something like wanting to store JSON-like data in a semi-structured document store like MongoDB or DynamoDB, if you want to store your structured data, you're primarily using some type of traditional OLAP data warehouse like Amazon Redshift or Snowflake. So the problem is now you have to, one, copy all of this data across all these different systems. Two, you have complexity for your data platform team because they have to now operationally understand and maintain all these different set of tools. Three is each system has their own way of enforcing governance. So the ability to say that this user has access to this set of columns or rows within a table. So there's no unified way of, across all these systems, trying to enforce access control. And finally, I think the most pressing is just it's very expensive to maintain all these systems, store data within all these systems, and both on a machine cost and a human cost. So fundamentally, if you think about the last 5 years, Open Lakehouse has now become very popular. The reason is because they've solved this problem of trying to separate out storage and compute. Rather than having to store data within all these different systems, you almost treat object storage as like a shared disk. On top of it, you have open file formats like Parquet or C, and then you bring these table formats like Apache Hudi, Apache Iceberg, Delta Lake. What these table formats provide is giving database-like guarantees. So they're the ones that are managing your collection of files. They allow you to specifically go back to a specific point in time within the actual data via like a time travel query. They enforce asset-like guarantees. And now you can use several engines, like let's just say an open source engine like Spark to go query this data. Or you can use a vendor solution like Amazon EMR to read the same table. So essentially, you're bringing different tools to your data, and you don't have to do these painful migrations. And the claim that we're trying to make, at least in this talk, is that Hudi, amongst the big three table formats, has just completely evolved to now what I like to call the AI native lakehouse. Essentially, it is being able to provide the primitives needed for users to basically store things such as vector embeddings, and by providing them a vector logical type, the ability to provide some kind of search, vector search API or SQL in order for users to get some kind of similarity search, the ability to store within a Hudi table blobs, things like image or video files, supporting other file formats outside of just traditional commoner formats like Parquet, like such as Lance, which is better suited maybe for AI and ML use cases, and then being able to store things such as JSON, which is going to be used via the variant type. So now instead of having to manage 5 different data systems, you can use this one technology and have it all be managed within a single view within a Hudi table. So at this point, I'd like to pass it over to Tim, who will be talking on our logical types.
All right, thanks, Rahil. So yeah, to kick things off, we'll talk about the variant. So it's probably something you've seen before. This variant type was added to the Parquet spec, and it really provides you some helpful utilities and performance on top of just shoving some plain JSON inside of a text field and instead of one of your columns. So, previously, if some data wasn't fitting an exact spec, maybe you just stored the raw JSON, parsed it at runtime, and just kind of dealt with it that way. But now, what you can do with variant is that you can store it as this new type, which contains some extra metadata, including what type of keys were present in this JSON blob. For example, the data itself is encoded in with a binary encoding. That also helps with some efficiency as well on the access side. And on top of all of this, there's also an option for what's called a shredded variant, where some of the fields will be extracted and stored as native columns inside of the Parquet file itself. So that helps a lot when, if you're familiar with Parquet, you've probably seen like the column level statistics. So with those shredded values, you're getting column level statistics that your query engine can use to speed up your queries for filtering needs. And since this is all defined in the Parquet spec, it's all standardized. Engines, like including Hudi now, have adopted it, and everyone should be speaking kind of the same language there with the variants. But for data that doesn't fit into the variant type, that's where we come to blobs. So for blobs, that's pretty much everything else. As Rahul was saying, you can have videos, images, basically anything that can be bytes, we can shove inside of a blob. It's our catch-all for everything that's not fitting into any of the other categories. So when we think of blobs, we think of two varieties inside of Hudi. We have what we call inline. So imagine that it's like more small payloads, maybe it's a free text box field or something that you're capturing. And the idea is that by inline, we mean we're storing that inside of the actual data file, or like what we call a base file inside of Hudi. Whereas out of line will be a pointer to something else inside of your cloud storage. So think like a pointer to some video in S3, or It can be also a pointer to a range within a file. So you can see in this reference here, we have like a reference to the file, and we can optionally include an offset in length. That allows you to bundle up various blobs inside of one file, so you don't have a ton of small files, and you just access based off of those extra fields. So you may be kind of wondering as well, okay, when would I want to use inline versus out of line? So think about just the implications of this. So as we said before, these data can be big. So for every base file in Hudi or any of these table formats, if you're familiar with them, there is usually some sort of cost associated with rewriting updates to rows. So for Hudi, after you merge on read table, have compaction, for example, you're going to rewrite that base file, which would cause you to reprocess all of those bytes. Can be extra transfer and overhead. So if you have large objects, it's good to hold a reference to those. So you're just pointing to something else in your existing storage layer. Or if you already have these videos or images stored somewhere else and you just want to start adding that references to them in your table, you can do that as well. So it's like maybe an easier way to migrate in your existing system to adopt this blob type. And then you're probably wondering, okay, if it's an out-of-line reference though, or a blob in general, how can I read back these bytes? So what we've done inside of Hudi is add support for, at least in the Spark SQL, we have this read blob utility here. It's backed by a Spark function they can also access. Just apply it directly to your RDD if that's how you're processing data. But just as provide some brief insights on this, the read blob will you lazily read back the bytes in the sense that we'll apply these filters. So you can see in our example query, for example, we have a in-stock filter. So we're checking for in-stock items before we render back all of these image bytes. It's kind of as an example. So the idea here is that we don't want to read everything. You don't want to eagerly materialize everything because that's a lot of I/O. It's a lot of processing overhead. If you're using Spark, maybe you want to do a join at some point with another table. You don't want to be shuffling all these bytes. So you generate a plan, and then the physical plan evaluates after the filtering there, so you can get back only the bytes that you need for your query. And then so for this, we leverage the reference and the position for the out-of-line data, and then for the inline, we are reading it from the file. There is, though, like some future work we're looking for being able to even treat inline data as a reference until the very last moment. And that's where things like Lance, the file format, come in handy. So Lance is a newer file format. I think the Lance project is really cool. If you haven't already checked it out, I would highly encourage folks to go read up on it. They're specializing in like fast random access, especially, and they advertise, and they also have a native blob type. And that blob type also supports lazily fetching out the data. So it's really cool. You can basically, the columns themselves are storing references to another block of data within the file that is the actual binary arrays representing your blob data. So it allows to lazily read back, just like we were doing with those out of line references. So for Hudi, you still do support Parquet. Obviously, it has its strengths as well. It's traditionally for BI and analytics workloads, and as a standard adopted by many query engines. And I think there's also a talk today as well about the evolution of Parquet in the AI world. So exciting to see what's going on there. But another advantage of Lance is that it has a native fixed size list type that's leveraged when you're storing vectors. So it helps, it does a better job encoding for these vector types, which are basically large arrays of floats. And I'll let Rahil take over and tell you more about how to use a vector.
Thanks, Tim. So yeah, I've been saying vectors a lot, so I'll try to give a clarity of what a
Rahil, as you do that, I do want to step in and just let people know we're going to move into a Q&A section very soon. So if anybody has questions, jot it down right now into the Q&A section or in the chat, and I'll be back in a couple of minutes.
Just one thing about the Q&A, we also have a demo, so I think I'll probably have to, just address the questions after.
Yeah, if we can move into the demo, that would be excellent. And then the questions you could do async.
How much time? Because I still have some slides, so just wanted to make sure.
If we could do like 1 or 2 more minutes for slides, and then we'll move on to the demo.
Okay, let me just very quickly then try to go through this so I can get the demo.
Okay.
So Okay, so for vectors, essentially, they're just a numeric representation of the image or video. You usually call one of these models to actually help generate the underlying characteristics of that image or document. And essentially, now that you have these vector embeddings, you want to be able to model them in some kind of logical type. In this case, in Hudi, we have now defined this kind of logical type here where you have it be a fixed array. And essentially, you can store either floats, doubles, or integers. And here's just some SQL of how a user would actually do this. Now that you have these vector embeddings in a Hudi table, you basically have the ability to perform a search on them. So what that means is if you were to plot these vector embeddings on some kind of mathematical plane, and then you run some kind of distance calculation, data that is similar to one another should be plotted nearby one another. And then when you run one of these search algorithms, which we will be providing, then you can be able to find relevant results to that particular image or video very quickly and accurately. So what that API looks like is basically this SQL function we're providing users. There's two modes. So the first mode is a single mode where if you have an image, you'll pass its query embedding. You pass the number of relevant results you want to see back, the distance algorithm you want to use to actually calculate this. And then for a batch mode, you can imagine, let's just say that you are a company that wants to show for each product, what are the other similar products to it. So you'll kick off this Hudi vector search and be able to find, all of these results kind of in batch. And we're using Spark to distribute this computation. So each executor is going to get a slice of the actual table, and we broadcast the actual query embedding to each of the executors, each one keeping its own local top K. And then when we want to pop back to the user the actual final results, the driver is going to aggregate this and then return a final top K relevant results. So now we can get the demo, which hopefully will tie this entire story all together. So I have right now running locally just a Jupyter lab, and I have some notebooks that will help kind of show the code in a more interactive way. So in this case, we're going to basically be showing our logical types, the Hudi vector search, and also the BLOB functionality. And like Tim mentioned, we have support for right now both Parquet and Lance. And you can run this demo. We'll have some links to this demo after the talk. So in this case, I'm using an off-the-shelf model over here. I'm going to also be using this famous Oxford PET dataset, so it's very easy to understand when we start visualizing things, what we're actually doing. And essentially, I'm going to first use this dataset and kind of sample 250 rows from it. I'm going to use some helpful Python libraries to help me when it comes to image embeddings, as well as with visualizations. I'm going to be using the Hudi binaries and also just setting up Spark over here. So now that Spark is being set, we are going to actually just take each of the images from that PET dataset. And for each one, we're going to attach some helpful metadata about it. And we're going to then run it through a model and get those embeddings. Okay. Now, at this point, we want to take this data and actually just have an in-memory representation of it within Spark. So I'm over here just right now defining a basically schema for all this data. In this case, I'm right now using my embeddings as an array type of floats because Spark doesn't have a vector type. And Spark doesn't have a blob type. So I'm representing this as just binary bytes for the images. Now, finally, I'm going to get to Hudi specifically because all this data is right now in memory, but we want to be able to persist this to disk and store this within a Hudi table. So in this case, I'm going to create my Hudi table. I'm going to define a blob column. I'm going to define a vector embedding column as well. And I'm going to now also insert to my table all of that data that we had in memory from the last step into this Hudi table. So now that we've inserted some data into the table, we want to be able to actually materialize some of this images. So in this case, I'll just run this query over here. First, actually getting the actual bytes and then wrapping it with the length to get the resolved byte count, and then also trying to visualize just one of the images within this table. So very quickly, I have right now, if you can see within my Hudi table, some structured metadata field. And then also within the same table, I can very quickly get back the raw bytes for that unstructured content. Finally, now I want to tie everything together with vector search. So say I pick a random image from this data set. It could be some random animal. And across this entire pet data set, I want to find the 5 most relevant animals in terms of how similar they look to that animal. So in this case, I'm going to use my Hudi vector search function. I'm going to pass a path to the table. You can also pass a name, the vector embedding column, the images embedding representation, how many results I want back, and then the distance calculation I want to use. So if I run this, in this case right now, the image that was my starting image that I want to find results for is a beagle, and it returned back to me the 5 most relevant images, some being beagles and some being some other animals. So let's actually visualize and see what this query returned back to us. So if you see over here, finally, so my original query embedding was this beagle, but across my data set, it found all these other images of beagles that look similar to this. You can also see that it didn't only pull back beagles, but other animals that have the same kind of characteristics in terms of its features, aesthetics, and looks as the original query embedding. So this is our demo. And we just have a couple more slides left on just what comes next for Hudi. So this whole entire vector search computation was what's known as a nearest neighbors, but it kind of involves doing like a full scan across the table and kind of distributing out to your cluster. So there's work to be done now to actually speed up this vector search by using what's called an approximate nearest neighbors. So we have an RFC or design out for that. We also want to be able to, within a single Hudi table, be able to store multiple file formats. So currently you either have your Hudi table being backed by Parquet files or being backed by Lance files. But I think for the future, it'd be very useful if we can kind of mix and match file formats for having structured content be in Parquet files and maybe unstructured content being in the Lance file. Similarly, we don't want to be super opinionated about the file format. In this case, we want to be able to allow our users to choose whether it be Parquet, Lance, as well as a new file format, which is Vortex. So we have work being done for supporting this file format. And then also, primarily, Hudi's current ecosystem has been very much focused in the JVM with things like Spark, Trino, Flink. So we already have a Hudi Rust connector to plug in with things like Ray and Data Fusion and supporting the same kind of unstructured storage primitives. So how you can get involved is you should definitely check out these 2 QR codes, which will be linking to the actual demo that was done, as well as some other helpful docs for how you can get started with AI use cases in Hudi. And then also, feel free to please check out the Hudi GitHub, Hudi Slack. Feel free to reach out to me over on LinkedIn or Hudi Slack. Happy to answer any questions or jam. And thanks also to these people as well for their contributions on this unstructured track. Thank you.
Thank you very much, guys. Sick demo, by the way. And you guys have a skill in introducing concepts extremely clearly. So I really appreciate it. If you can, both of you, if you can put down your LinkedIns maybe in the chat too, that would be useful. And maybe even just like that last slide with the QR code, how to get involved and how to contribute to Hudi into the community. We can put those in the chat below as well, so that it's easy for everybody to get started. And thank you guys, Rahil, Timothy. I appreciate it.
Thank you, Anna.
All right, thanks, guys.